Okay, so our class is now being recorded. Once again, good morning, everybody, and welcome to class number 9 of our course on Network Fundamentals for Cloud. I'm sharing my screen now, and we are ready to begin. Okay, so this is where we left last time. Quickly, if you want to recollect what we discussed in the previous class, we actually were on the topic of data center networks, and we saw a very quick short video about what is a data center network, where we saw the Google data center network in action. We talked about the application network dance and how the network evolves based on the evolution that happens to the application. It's not the other way around. The application leads this dance. We talked about the northwest and north, south, and east-west traffic, and we noted that in any data center, the east-west traffic is much more, or the server-server traffic is much more compared to the north-south or the client-server traffic. And this we also noted from the Facebook case study, where the same observation was very clearly highlighted. We looked at the key challenges that exist in data center networks, particularly the fact that the traffic that a data center network handles is extremely huge, considering the fact that it's still on the edge of the internet and is actually an access network. The traffic that from an access network standpoint, the traffic that it observes is extremely high for any sort of an access network. And not just that, we talked about why the deadlines for traffic exchange over the data center network are extremely tight. We looked at the challenges of congestion in the data center network and the specific peculiar problem of TCP incast. So in this slide, we had looked at why we claimed that the internal traffic is very, very huge by looking at some sample numbers that existed in 2020 and with an estimate that every year the traffic grows 5 times. Okay? And this was a key fact that we noted that the east-west traffic accounts for more than 90% of the total traffic. So it's server-server traffic which is predominant in a data center network. We had concluded by quickly summarizing the issues that exist in the infrastructure side. And we said this may not be too much of a concern to us, but for the sake of completeness, we did note that the networking cost is a challenge for the designer of a data center network, because you have to keep the cost into consideration when designing the data center network. Also, the cooling has to be designed in a fashion that where there are thousands of servers running, the heat produced is enormous, and the cooling has to be planned. The cabling has to be done in a very planned manner, because when you connect thousands of servers together, you don't want the cables to be just hanging around. So cabling is a very important factor in data center network. So this is what we had talked of last time, and this is where we had stopped our discussion last time. Today we will, after having taken that brief overview of how the data center network looks like and what is the nature of traffic that it observes, we will talk about how the data center network itself has evolved in the last decade or so. Okay, so even before cloud computing came into picture, data center networks have been there in limited capacity for serving the private needs of a single enterprise. So large enterprises, even in the past, even before cloud computing, did have a lot of servers that were needed to run the business processes of an enterprise. And these servers were often placed inside the private data center of a large enterprise, connected together via a data center network. Okay? So the idea of having a data center where the servers and the storage devices are connected via a data center network is an old concept, is a slightly old concept. But with the advent of virtualization technologies and the virtualization of all forms of resources that exist in a data center, servers, storage. We entered into an era which we today see as the cloud computing era. So it's not just that the data centers are today limited to or restricted to private enterprises, but public infrastructure service providers have taken the model, built data centers which have resources like servers and storage that can be shared amongst multiple tenants, creating a public shareable resource pool of infrastructure. Now, virtualization enables you to create virtual instances of the infrastructure and share the virtual instances of the infrastructure amongst the different tenants that exist who are sharing the data center resources. So over a period of time, from private data centers to public data centers, from physical servers connected via physical data center network to a model where we have virtual servers connected to virtual storage and all together connected via a virtual network. We've come a long way from how data center networks looked like a decade ago to what they look like today in the era of cloud computing. So this part of our course where we talk about data center network evolution, we'll look at what was the oldest topologies used in data center networks, right? And then how they started to have challenges as the applications evolved. What is the current data center network topology that is followed in the modern data center? And how these topologies help enable or solve the challenges that we discussed in the previous class. Okay, that's what we are going to cover in this part of it. So as I summarized, this slide summarizes all of that. When we start with the traditional network topology, we'll talk about a topology which is called the access aggregation core. This is the traditional topology that was followed almost 7 to 8 or a decade back in data center networks. In the access aggregation core topology, we'll start with this. And as I said, it became prominent almost a decade or so ago, around the year 2000. At that point in time, because it was largely designed to cater to large enterprises which had their own private data centers, the concept of virtualization was not so much. So it was a technique used to connect physical servers together. It was a cheap, easy to administer, and a fast method of creating a network data center network topology. Okay, and because the applications in year 2000 and so were still not the cluster-based distributed applications that we talked of in the last class, the predominant traffic that the data center still saw in the year 2000, 2005 was the client server traffic, because that was the era when web applications were becoming extremely popular. The Internet of Services, the second generation of the internet, was becoming prominent, where e-productivity, e-commerce applications were evolving and being administered via these data centers, were being serviced via these data centers and the servers that resided. So it was predominantly the client server application traffic, and mostly the north-south traffic pattern was what was observed, and the access aggregation core topology that we will talk about was very well suited to this kind of traffic pattern. But as we saw last time, applications evolved from pure web applications to more complex microservice-based architectures, clusters of servers brought together to build distributed server-based applications. And this meant that the traffic suddenly changed, or gradually, not suddenly, but gradually changed from being predominantly north-south traffic to becoming predominantly server-server traffic. And that was a big change, because it meant that the existing network topology, which was built to cater to the north-south traffic could no longer cater to this evolved scenario where the server-server traffic was much more than the north-south client-server traffic. So we evolved gradually from access aggregation core to the modern DCN topology that we have today. It wasn't a sudden shift from access aggregation core to what I'm going to talk about in modern DCN topology, but it was a gradual migration, step by step. Certain things happened in between. Some technologies got introduced to solve some of the problems and challenges, but eventually, every intermediary step that we came up with hit an issue as the server-server traffic continued to grow. So if you look at the current topologies which exist in a data center, which we are calling as the modern data center network topology, this being the final step. So if I say this is the first step from where we'll start our journey, the access aggregation core. This is our final step. This is where we are today. Okay? I'll first talk about what the first step was, then I'll talk about where we are today. But in the next class, I'll actually trace this journey path. Okay? So once today, we'll actually just try to look at what was the case with traditional networks when it was predominantly client server traffic. Then we'll look at what is the case today when it is predominantly server-server traffic. So this should give us the starting point and the end point of the journey. But the next class, we will try to trace this journey as to what happened in between this from access aggregation core to where we are today. How did we reach that state? It wasn't a sudden shift, but it was a gradual change, and that is what the whole journey we will talk about in the next class. But today we will talk about the access aggregation core topology and why it became challenging to continue or persist with this topology with modern applications. What is the current topology used in modern data center networks, which is actually a base. It's a new structure which is based on a topology that is called the clause topology. Okay, it's named after the inventor of the network topology, Charles Claus. And we'll see that what Charles Claus defined as a communication network topology. When he defined the topology, he did not even have data center networks in mind. He actually defined it for circuit switch telephony networks. But as the modern data center network requirements grew, we realized that the class topology, which was designed for circuit switch networks, was actually very suited to the modern data center network needs. Okay? So the basic fundamental foundational block for modern data center network topology is the class topology. Class topology has various forms. Class is a concept, it's an idea, it's a structure, it's a building block. But there are variations of the class topology that exist in modern data centers today. One of the very basic class topologies that we will study to some extent is called the leaf-spine topology. And we'll see that the leaf-spine topology is what modern data centers networks use extensively. They've evolved it to more complex variants of the basic leaf-spine topology. And that is what we will look at when we come to these case studies on Facebook's data center network or Google's data center network. We'll see how they've tried to pick up the leaf-spine topology, which itself is a basic class topology, and evolved it to more complex data center network topology using leaf-spine as a building block. Okay. But there are other variants of the class topology as well. Fat tree topology is another special instance of the basic class topology, which is also quite popular when you look at modern data center network. Okay. So this is what we will talk about broadly today's class. And next class, we will try to trace the journey between the first step, where the access aggregation core, to where we are today, which is the class topology. Okay, so let's start with the traditional data center networks. what existed in the year 2000, 2005 period, when the majority of the traffic was client server traffic. The data center used to be more of a private enterprise data center. The servers used to be primarily physical servers, and virtualization was not so much of a thing. So it was physical servers hosting web-based applications with their three-tier architecture, which I talked of in the last class, the web tier, the application tier, and the database tier. And predominantly, traffic, which was basically originated from clients using the services of this enterprise, originated from all across the globe and therefore was mostly from outside the enterprise. Okay, so this is where, let's say if I say www.amazon.com or the e-commerce platform amazon.com, you can say that these are those physical servers hosting the Amazon marketplace, the e-commerce platform. But bulk of the traffic that reaches these servers is coming from outside the enterprise, outside the Amazon enterprise, from users of the marketplace who sit all across the globe. So it's predominantly north-south traffic, client-server traffic. So the access aggregation core, the term access aggregation core comes from the fact that the architecture of the traditional data center was actually a three-tiered architecture. If you look at it, you will find it very, very close to what we discussed when we discussed the internet topology. What did you see in the internet? We saw that the internet was a collection of it's a network of networks where edge devices, if you think of physical servers as edge devices, then edge devices connect to an access network. The home network, the mobile network, the enterprise network. The access network connects to the ISP network, Internet Service Providers network. You can think of the Internet Service Provider because the Internet Service Provider services a lot of tenants or a lot of customers. The ISP network is aggregating traffic coming from multiple access networks. So if multiple people are taking service from the same ISP, all the home access networks are getting aggregated in the ISP network, thereby kind of making the ISP network like an aggregation network. But then you had these national ISPs and the global tier 1 ISPs who formed the core of the internet. We also called it the backbone of the internet, which connected the smaller ISPs to each other via the tier 1 or national ISPs, and therefore made the internet a connected network. Okay? Now, if I blow down that three-tier topology of the internet, the access network, the aggregation network, the core network, into a single enterprise data center network, you see the same three tiers existing as three layers inside the enterprise itself. So the first point of contact for these physical servers, or the connection point, was the servers, is the set of switches which are called the access switches. So instead of the network, the access network, you have the access switches, which are connecting the physical servers to each other, along with building some level of redundancy. I need redundancy because if I have only one access switch and that access switch goes down, then my servers become unreachable. So I have some level of redundancy, which we will shortly talk about. What is this level of redundancy? But some level of redundancy built in so that single network failures do not lead to reachability issues to the server. Right? So the first line of switches that connect to these physical servers was the access switch. The access switches then connected to a next tier of switches, which were actually more complex, larger switches with more number of ports called the aggregation switches. Again, the term aggregation largely indicating that these switches play a larger role. They handle more traffic than the access switches, and they aggregate traffic from multiple access switches, just like an ISP network would aggregate traffic from multiple access networks. Right? And even these aggregation switches existed in pairs in redundant configuration so that failures, single point failures, did not affect the entire data center network from going down. So inside of the enterprise, the predominant method of connection, because you can see this like a local area network. And when we discuss the general network fundamentals, we've talked about a local area network being predominantly connected via layer 2 switching technologies. Okay? That's what happens in the access networks in the internet. Your local area networks predominantly use layer 2 switches, MAC switches, Ethernet switches, to create a layer 2 switched network. Okay? And that's what we see even in the traditional data center network topologies. The access switches are actually layer 2 switches. They're like your standard Ethernet switch. Everything below the aggregation switch, when it communicates to the access switches. Similarly, the access switches, when it communicates with the physical server, it's all layer 2 switching. Right? So when I say layer 2 switching, what do I mean? I mean that you're looking at the destination MAC addresses. MAC address is a layer 2 address. To switch the traffic at the data link layer, the layer L2 of the protocol stack. That's what you see below the aggregation switch. But eventually, the client server traffic, as we said, is coming or going out of the enterprise to the rest of the globe via the internet. Just like sitting at home, you are mostly trying to access the internet. So your traffic goes out of your home network or the local area network to the wide area network, which is the internet. And as we discussed earlier, we had made this point that whenever your traffic goes out of the local area network into a wide area network, you have to rely on layer 3 routing technologies to forward or route that traffic towards the destination. The internet forwards traffic based on layer 3 protocols, the routing protocols. That's what we've learned in our first 5 or 6 classes in this course. So the aggregation switches had a third layer of communication, which were called the core switches. So the core switches are basically the ones which are receiving and sending all the traffic from the external internet. And every traffic that comes from external internet is what? This is layer 3 IP traffic, which is coming to the enterprise network via a method of routing using the destination IP address. Okay? That's how the traffic has reached the enterprise, by following a process of routing across the internet from some source across the globe to be able to reach a particular destination IP address that resides within this enterprise. Okay, this IP address could be the IP address of this server over here, let's say. Okay? So the traffic has been routed. The core switches are the routers. These are not switches, but you see the circular notation. These are the routers which are receiving IP routed traffic from outside the enterprise to the core. And this is what they are forwarding towards the aggregation switches. So the aggregation switches play that intermediary role where they connect using a layer 3 routing protocol to the core switches, but connect using the layer 2 protocols to the access switches. You think of the aggregation switches as an adaptation layer in between the external L3 connectivity and the lower L2 connectivity. And this cloud that you see between is a private is the private IP network of the enterprise. Okay. So this is a layer 3 network. It's an IP network. So this is where the aggregation switches and the core switches are exchanging IP packets, which have to be sent outside the enterprise towards the internet. And that is why we are this 3-tier architecture that gets its name. The access aggregation core topology comes from the 3 tiers of the network topology. Okay, so essentially, this is what we've said. The servers connect to the access switches at the lowest level. The access switches connect to the aggregation switches at the next level of hierarchy. So the aggregation switches are aggregating across the data center. The data center could be, because it's a large enterprise, it could be wide and huge. Multiple racks of physical servers, and therefore multiple access switches getting aggregated at the aggregation layer. It's still a layer 2 network. Right? So within, if at all I need to send traffic from a server A to a server B, it still goes to an access switch, to an aggregation switch, to another access switch, and then to a server. And all of this is what? Layer 2 switched using MAC address. So this is a layer 2 network still. Internally, all traffic from server A to server B will still be L2 switched. Okay? But if there's a traffic that needs to go out, the aggregation switch will convert it into IP traffic, send it towards the core router, which will then, it's like a gateway, border gateway to your network, implementing the BGP protocol with the external autonomous systems. Right? And this will send it towards the outside of the internet. So the aggregation to core connection is basically for all the external traffic that goes out of the enterprise. This is how traditional enterprise specific data center networks were set up, created. So everything internal, like a local area network, is L2 switched or L2 bridged. Everything going out from the enterprise is routed, layer 3 routed. Now, why did I say, if you remember on previous slide, I said these topologies which came up in year 2000 primarily to cater to client server traffic or web-based traffic and support e-productivity, e-commerce, web applications and services. This topology, I said, was cheap, it was fast, and it required very minimum configuration to set it up. It was easy, is the term I had used. The reason that was the case was because internally, inside the local area network, we were not bothered about using routers. Right? Routers are costlier than a switch because of the multiple control plane functions that come in the network layer of a router. It makes the router more complex and more costly compared to a basic switch, a layer 2 switch. So the local area network can be set up in a low cost manner using just switches rather than routers. 2, it's fast because we don't have to go to the third layer of your network protocol stack in order to do a routing table lookup before deciding where the packet has to be forwarded. I mean, I'm talking about internal traffic going from A to B and inside the enterprise. I don't have to look at all this. I don't have to go to layer 3 of the protocol stack to route the traffic. My traffic can be received at a switch, handled at the layer 2. Right? So the amount of encapsulation, decapsulation that's happening is lesser. You're able to do the forwarding function at the layer 2 itself using a switching table. When we talked about SDN, we saw that many of the lower layer functions are often implemented in hardware. So Ethernet switches have a lot of hardware-driven switching functions which can make the switching function extremely fast. Using table lookups that can happen in hardware or in ASICs. So it's faster than IP routing. And third, it's zero touch configuration. That's what we call it. Layer 2 networks can be set up with zero configuration. You don't need routing protocols. Layer 2 networks are what are called as self-learning network. Why is it a self-learning network? Because let's say A has to send some traffic to B. What will A do? It will create a layer 2 frame, right? A layer 2 packet with a destination MAC address DM, destination MAC address DM, a source MAC address SM. So SM is the MAC address of A, DM is the MAC address of B, and then the remaining fields in the layer 2 frame. Now, when the access switch gets this frame, layer 2 frame, it sees the destination MAC address DM. Now, it looks up a self-learning table. So every switch maintains a table which actually it is learning by observing the flow of traffic on the layer 2 network. What is this table? This is the same forwarding table that I talked about. Okay? But at the layer 2 level, we said you have the destination MAC address and you have the outgoing interface on which the packet has to be switched. This is your regular forwarding table. But at the layer 2 level, right? Looking at the layer 2 address. Now, how is this table manually self-learned rather than being created via a routing protocol? So in the layer 3, the routing table, which we had talked about, it's also a forwarding table where instead of the MAC address, you have the destination IP address and you have an outgoing interface. But this forwarding table we saw got created using the routing protocols in the control plane. However, the switching tables, so this we called as the routing tables. Whereas in switches, the switching table, which are also forwarding tables, but at layer 2, they are not created or populated using any form of routing protocol. You don't need routing protocols to create these switching tables because the underlying assumption is that a local area network is a smaller network, not a huge network like the wide area network or the internet. In a smaller network, I can rely on broadcast methods and the ability to observe the flow of traffic in order to learn which node is reachable via what interface and automatically via self-learning populate this table. So coming back to that example where I said A has to send some traffic to B. A creates a frame, sends it to access switch 1. This is switch 1. Switch 1 looks at DM, the destination MAC address, goes and consults its forwarding table. Maybe let's assume for now it doesn't find a match. It doesn't have an entry in this table for DM. What can it do? Because it doesn't have an entry, it can simply broadcast that message or that layer 2 frame in the entire layer 2 network. Okay, so that let's assume for now that this frame gets broadcast in the entire L2. So it will go to all switches. It will reach all switches and all switches will forward it to all servers. It's basically a broadcast to every person, every server in the network. Now, when a packet is broadcast, every switch, whether aggregation or access switch in the network, sees that packet. What does it learn? It learns that the source node SM is reachable via the interface through which this broadcast packet arrived at the switch. So what I'm saying is, let's say, if this is the interface using which the packet reaches the access switch, what is the access switch going to make an entry of? It will say destination MAC address SM can be reached via interface A. So let's call it A, B, and C, these three interfaces. It's learned. Okay? When the access switch sends the traffic, let's say, to the aggregation switch, the aggregation switch will also learn that source MAC address SM is reachable via the interface through which the packet arrived into the switch. So gradually over a period of time, the broadcast traffic reduces Because of the self-learning property, and the unicast traffic grows because these switching tables get populated on their own. So layer 2 networks don't require routing protocols to populate the switching tables. They follow a self-learning protocol. And the self-learning protocol relies on broadcast as the underlying means to learn. And broadcast works because local area networks are smaller networks. And therefore, broadcast can be done. If they are very large networks and everybody is broadcasting to everybody, then there'll be a huge amount of broadcast traffic in that network because every node is sending to every other node. And the number of nodes, if they are in thousands, the broadcast traffic becomes enormous. The network resources get blocked handling a lot of broadcast traffic, which is not ideal. But in a small network, you can rely on broadcast. And rely on broadcast and then employ self-learning to eventually learn of all destinations and how they are reachable, fill up your switching tables, and eventually all traffic becomes unicast or switched. This is how layer 2 networks learn on their own. They are self-learning networks. And that property of the self-learning property of layer 2 networks makes it zero configuration. Okay? So these are three things that are very important. Why did I go for a layer 2 bridged access network? Because of silicon switched packet forwarding. Silicon switched means more than hardware, which could make it extremely fast. Because of my ability to use switches instead of routers. And therefore, also you have the ability to have some proprietary methods for forwarding of traffic. I'm calling it a proprietary enterprise protocol stack or a network stack. Because my traffic is not going to a wide area network, to the internet. Internally, I can use proprietary protocols also. It's all within my network. So I could make it simple, I could make it fast, and then I could make it quickly working. I can just install these network elements and without any configuration. I don't need to provision static routing in my routing tables even. It's self-learning. So zero configuration, I can get my network up and operational. And this promise of zero configuration, which means you don't need an administrator to bring up your network. You just connect the things, turn them on, and they learn on their own, and they start working, was a very promising thing at the point in time. Okay, is this so far clear to everybody what we've discussed? Does it make sense? Because this is kind of borrowing the ideas that we've discussed so far about internet, applying them to a data center network. The same ideology, the same concepts. We've just shrunk the scale by saying, okay, we're not talking about access networks, ISP networks, and the core of the internet. We are talking within a data center, but it sees a high volume traffic. So we are designing it like a mini internet with access switches, aggregation switches, and core switches. But internally, just like LANs in an internet use layer 2 networks and layer 2 switching, we are also using layer 2 switching in the core, in the inside of the enterprise network. But whenever traffic has to go out to the internet, yes, it's common sense. We need IP traffic. Therefore, layer 3 routing comes into picture there. But the inner network is very fast, extremely fast and quick and zero configuration. Does that make sense for everybody? Yes, no? Okay. Try to understand these very, very closely because this whole evolution is where you will learn why this thing worked earlier but became a problem later. Okay, so thank you, Ravi, for saying yes. Right, because if there's anything not clear, then you should ask, put a question on the chat, ask. Right? But I think this should be clear because it's kind of borrowing everything that we've discussed from our fundamental sections. So that's what a traditional data center network topology looks like. Now, what we will though talk about now, while we've said, okay, these bridged networks, have a lot of advantages. They are fast, they can be built in a proprietary fashion at low cost, and they are require zero configuration. That's their benefit. Bridged network topologies in local area network also have certain challenges. Okay? Layer 2 networks have their own challenges, which we need to talk about. So one of the challenges that exist in layer 2 networks is as the layer 2 networks start to grow. Right? So if you remember when we talked about virtualization, we talked about VLANs, virtual local area network. The reason why virtual local area network evolved as a network virtualization technology many years before cloud computing came into existence was to solve the problem of broadcast storm. When I discussed VLANs in the 2 classes back, I mentioned that the issue with larger layer 2 networks becomes that the broadcast traffic starts to grow. When you have multiple departments, computer science, electrical engineering, core engineering, management, so and so on forth. As the layer 2 network grows, the broadcast traffic starts to create what we call as a broadcast storm. I mean, it's a storm in the sense that it's a huge volume of traffic that is now flowing into your layer 2 bridged network or switched network. Right? So it's unnecessarily wasting a lot of your network traffic, network bandwidth. Broadcast is a wastage of network bandwidth. Ideally, I would want everything to be unicast because it just takes the bare necessary bandwidth of the network to send a packet from a source to a destination. As soon as I use broadcast, I'm wasting the network bandwidth because eventually the packet has to go to only one destination. So broadcast storm is a wastage of network bandwidth and network resources. And as the network grows, the broadcast traffic exponentially starts to grow. So we had talked of in that class a solution to this problem by saying that, okay, if I still want to keep it as a layer 2 switched network, but wish to bifurcate it into sub-networks to limit the broadcast storm, what is the solution we built? We used the solution of VLANs, virtual LANs. We said, okay, let it be a large layer 2 switched network at the physical layer. Physically, the network can be a large L2 switched network. But on top, by using a field called VLAN ID in the layer 2 frame, I can artificially create multiple virtual local area networks and limit the broadcast traffic to within a local area, a VLAN. But when there is traffic that has to go from one VLAN to another VLAN, we can actually have the routing functionality come into picture, and across VLANs, we can route traffic, just like I would do between 2 local area networks. Correct? So that's a solution we had talked of. VLAN as a big solution. Another way in which you can limit your broadcast traffic, not just so STP I have yet not come to, Ravi. I'm coming to that. I've right now just re-emphasized on the need for having VLANs, which we had covered 2 classes back. Now I'm saying that, okay, while VLAN is one solution to address the issue of broadcast storm in layer 2 switch networks, an alternate technique, sometimes also complementary technique. Complementary in the sense that it's not as if if you use spanning tree protocols, you cannot use VLANs, or if you use VLANs, you cannot use spanning tree protocols. In fact, later we will see that we eventually ran into a need to have both of them together. But for now, let's talk about spanning tree protocol in isolation. It can be seen as an alternative to solve the issue of broadcast storm in layer 2 bridge network. Now, what is a spanning tree protocol? When you look at a layer 2 bridged network, like the one on the previous slide, On this slide, what is this? Everything below here we said is layer 2 switch network. It's a layer 2 switch network. Do you see a lot of cyclical paths and redundant paths in this network? Yes, because that is how the network's been designed to be redundant. If one access switch goes down, oh, by the way, I forgot talking about that. Everything that you see will exist in pairs. That was the important thing I wanted to mention. So access switches exist in pair. Aggregation switches exist in pair. So there is what we call as a 1:1 redundancy at every layer. 1:1 redundancy. Okay. Every switch, every router has a redundant tier so that if it goes down, the other one can handle. And therefore, if you see the connectivity also, 3 servers in this rack, let's call it rack 1. They are connected via 3 physical cables to 3 ports of access switch 1. But they're also connected via 3 separate cables to access switch 2 as well. Similarly, look at the physical servers of rack 2. They're also connected to both access switches via a pair of communication links from each server towards the switch. So we have communication link redundancy. We have network redundancy in the form of access switches. Any single point failure will not cause the network to go down. But what is the cost of this redundancy? Especially when you look at broadcast traffic. The cost of this redundancy is in the cycles or multiple redundant paths that you have between any pair of servers. So pick a server A and a server B in this architecture. How many paths do you see from A to B? Maybe the first path goes via access switch 1, aggregation switch 1, to this access switch, and then to B. Another could go via access switch 2, still aggregation switch 1, and then this. Third could go via aggregation switch 2, then access switch 1. So you will see there are multiple paths between any pair of servers in this network. While that is good from a redundancy standpoint, what is happening when you have broadcast traffic? The same traffic, it's getting duplicated, triplicated, quadruple times. It is reaching the same destination B from multiple paths because it's broadcast. So redundancy in the network, while it's good from a network, from addressing network failures, when it comes to broadcast traffic, it is growing or blowing up the broadcast storm. Correct? Because of the multiple redundant paths that you see. Also cycles. Okay. The second thing that you should observe is not just the redundant path, but the fact that you have cycles in this network. Okay? So if I send a broadcast traffic from server A to access switch 1, and let's say access switch 1 sends it to aggregation switch 1, aggregation switch 1 sends it to aggregation switch 2, aggregation switch 2 happens to send it back to access switch 1, access switch 1 has no way to check that it's the same traffic that it had originally received. It sends it back again to aggregation switch. What have I created? A cyclic path. You will find multiple such cycles in this network. So broadcast traffic can continue to keep flowing in the network in cyclic loops, stuck in cyclic loops. And that is why the other reason why we call it a storm. It's like a cyclone. Right? You've seen a cyclone or a tornado having concentric cyclic paths in which the whole storm is actually created. That's what is happening inside a layer 2 network, which has so many redundant paths. Because of those cyclic paths, the broadcast traffic keeps on going on and on in the network until it can eventually be discarded. And that's one of the challenges of bridge network topology. So bridge network topologies use a protocol called spanning tree protocol. Right? We need the redundancy. When there is a fault, I need a redundant path, right, to be established. But what I don't need an active configuration. I can have an active standby configuration. Only when the active path fails do I need a standby path. The spanning tree protocol does something like that. So if I have, let's say, if I redraw the previous topology between A and B, and I say there are multiple paths to go from A to B via two different access switches, access switch 1 and access switch 2. It's similarly from B to 1, I have multiple paths. This is, let's say, the physical network. But what will spanning tree protocol do? It will translate this topology into a spanning tree. Right? It will say, okay, the dark ones are the active links. And the dotted ones are the redundant links, which I will use for traffic for forwarding only when there's a failure on the primary link. So what have I done? I've said, okay, the physical network topology is designed for redundancy. But the spanning tree protocol has artificially marked some of these links as standby links, so that I can remove the cycles in the network and broadcast traffic doesn't keep flowing into cycles and create a storm. But eventually, what have I done? I've created. So look, you can call this a graph data structure. This is a graph. And what have I created with these solid lines? I've actually created a tree. Every node is connected via a path. But what is the property of a tree data structure? A tree data structure is acyclic in nature. There are no cycles. A graph can be cyclic. A tree is always acyclic. So this was only two nodes. If you look at the previous slide, for example, where there are 3 servers in each rack, you have total of 12 nodes. You will create a spanning tree between these 12 nodes by creating, let's say, solid links between all of them and saying, okay, this is the spanning tree protocol. This is the spanning tree that helps me connect all nodes to each other. The rest of the links are all dotted links. They're all standby, only to be used when there's a failure. So the spanning tree protocol is a very important protocol used in layer 2 networks, which recognizes redundancy in the network, retains that redundancy for failures, but creates an active network topology, which is a spanning tree structure. So every node is reachable to every other node, but only via one path. The dotted path is only for redundancy when there's a network failure. And when a network failure happens, the spanning tree protocol detects that failure. It runs again. It looks at the standby paths and recreates the spanning tree. So let's say if this link was to fail, the spanning tree protocol will create a solid line to A2 and then a solid line to this, recreating a new spanning tree, but always ensuring that there is no cycle in the entire path, because now this path has gone down. So there is no cycle. I'm now using a redundant path. So spanning tree protocol, like a routing protocol, is always running, constantly running, detecting network changes, faults in the network, rerunning to recreate new spanning trees, but at the same time avoiding any cyclic paths. Basically saying that they're translating a network graph into a tree structure, network tree structure. Okay, so spanning tree protocol is an alternate solution that you can use even without creating VLANs to solve. Now you can have one physical layer 2 network, large network, and with spanning tree protocol, you can still avoid the challenge of broadcast term. Okay. VLAN you will create when you want to have separate administrative domains like the computer science department and EEE department. That's VLAN is preferred. But if it's a one administrative domain, the challenge is broadcast term. Spanning tree protocol solves that. Okay, again, makes sense. Now, is it clear, Ravi? What spanning tree protocol is? Converting a network graph structure to a network tree structure. That's what STP does. Now, when STP functions in layer 2 bridge network, we saw that it does away with the redundant links by marking it as standby links. So what it means for our access aggregation core data center network topologies is that all the duplicate redundant links that you can see in this diagram, while they exist, the bandwidth available on those links is not being utilized. So in a different world, you can actually say that it's also not a very elegant solution is by use of spanning tree protocol. Okay, okay, Ravi, I get it. Yeah, thank you. But now it's clear, so that's good. So what happens as a result of the spanning tree protocol is that the redundant links are not at all being used, which also means that the network bandwidth which are provisioned on those links is also being underutilized or not utilized at all. So essentially, we are saying that yes, broadcast term is a challenge in layer 2 bridge network topologies. It can be solved using spanning tree protocols, but what it results in is that the access aggregation topology that we see in these traditional data center, it can only work as active standby. Most of the redundant links will get marked as standby. So the provisioned bandwidth on those standby links is actually not being utilized. It's also in a way wasted bandwidth. There is some bandwidth on those communication links. I could have used it, but because it resulted in a broadcast term, I could not. Spanning tree protocol prevented me from using those links. Okay. Now, what if we wanted to use these alternate links as well more meaningfully? Utilize the bandwidth that is there on those links as well, and yet not have the challenge of broadcast term. What can I do? I can use both these techniques that we've talked in these two classes. We talked of the concept of VLAN as one of the methods of dividing or bifurcating a layer 2 network into two virtual layer 2 networks. But right today we talked about spanning tree protocol, which without doing any form of a bifurcation of the layer 2 network is actually marking certain links as standby and creating a non-cyclic tree structure. But what if I can use them both together? So what I can do is I can first split my layer 2 network into multiple VLANs. And then I can say that VLAN 1 uses one spanning tree protocol. VLAN 2 uses a different spanning tree protocol where in such a way that the primary links being used by VLAN 1 are dotted or secondary standby links in VLAN 2. And the primary or active links of VLAN 2 are actually the dotted or the standby links of VLAN 1. Do you get what I'm saying? So rather than creating a spanning tree at the granularity of the entire LAN, local area network, I first split it into two VLANs, let's say VLAN 1, VLAN 2. And then I individually create a spanning tree protocol for each VLAN given the constraint that VLAN 1 and VLAN 2 use mutually exclusive links. Now, if I can do that, then I can actually arrive at a solution where all links of the network are now being utilized. So no communication link bandwidth is remaining underutilized. At the same time, there is no broadcast now. Because when you look at one VLAN, it is still a spanning tree. You look at the other VLAN, it's still a spanning tree. But when you superimpose the two spanning trees on each other, all links in the physical layer 2 network are being utilized. So I have complete utilization of my network bandwidth. At the same time, I have avoided broadcast. Is that clear? I'm taking a pause. Did you understand how we used VLANs plus STP together to create a per VLAN spanning tree in such a fashion that we could adequately use the network bandwidth and still avoid a broadcast stop? Correct? And of course, even if I want to individually use VLANs as an isolated solution alone without STP for reducing flooding and broadcasting of broadcast packets, that we can always do, like we discussed in the previous class when I discussed VLANs. VLANs naturally have the effect of limiting the flooding because you're creating two separate layer 2 broadcast networks by using VLANs. Okay, so VLAN can be used as an individual independent technology. STP can be used as an independent solution. But what we see in traditional access aggregation topology is actually the middle ground. We use them together so that I can use the network bandwidth as well as prevent broadcast. So this is what traditional data center networks were doing when they were using the access aggregation core topology. Okay, it's 1 hour boundary. I will take a break here. If anybody has a question in the meantime, during this break, you have the time, you have 5 minutes for the break. Post a question on the chat. When we come back after the break, I'll probably first address those questions before moving forward. Okay, so it's 11:33 by my watch. Let's take a 5-minute break, come back at 11:38. Meanwhile, anybody has a question, post it on the chat. We'll start again at 11:38. Okay, I think it's 11:38. Back from break. We have one question from Ravi. Uh, Everybody can actually read that, and then another one from Ajit, which we'll come to. So Ravi is asking if what we've looked at is from a how do you control system is flooding broadcast messages. So far, we've discussed on controlling flood at network configuration end. How about at system end we can do? So actually, if you look at spanning tree protocol, Ravi, it's a system level protocol resulting in a particular network configuration. So it's a protocol that collectively, it's like a routing protocol, it's a distributed protocol that runs on all the network nodes, the switches in the network. So it's a system level protocol that runs on all nodes, all systems in the network in order to create a spanning tree. The resulting configuration is a consequence of the spanning tree protocol. So in reality, you should see it as a networking protocol or a system level protocol, which is solving the problem of broadcast traffic. And further to your question about if redundancy, if there are multiple network interface cards are teamed together for redundancy, will STP still work? Yes. So multiple network interface cards means multiple communication links from the same device to the same switch. There may be two redundant links via two different network interface cards. STP will still treat it like two links, and it is able to handle that as well. So it will mark one of them as active, the other as standby. So yes, STP does cater to those situations also. Ravi, since your system means is laptop or PC. Oh, you mean the server side? So you mean is this server able to address that as well? Yes. So the servers are included in the entire communication path. So the servers, actually, if you look at the servers, they also have that layer 2 implemented, right? The entire protocol stack is there in the server. So the data link layer in the servers can also do implement the self-learning property and the STP protocol. So all nodes in the layer 2 network are involved in running the STP protocol. So it's actually the access switches, aggregation switches, the servers, all of them participating in this setup. Okay. Ajit has a second question. Is there any inter-VLAN communication here with STP plus VLAN setup? If yes, how to handle that? So as I said, Ajit, when you have inter-VLAN communication, that's handled via the layer 3 routers. So when you create two VLANs, it is like having two layer 2 networks. And to connect any two layer 2 networks, the only way is to use a router, intermediary router in between. Okay? So in that case, the traffic will get routed through the two VLANs. Okay? So the core router or the aggregation switch also, which has the L3 functionality, can act as a router to route the traffic across two VLANs. Okay. So Ravi, what do you mean by, so if servers flooding the broadcast messages? Normally the servers don't flood. They will send it over one of the interface towards the access. The switches are what implement the broadcast function. But the STP protocol is being run, can be run in the servers as well, so that if there are redundant links, let's say this link and this link, that can be discovered and only one of the links is marked as active, the other is standby. So the server will only send the layer 2 frame over one of the links towards one of the access switches. Okay, I think that's what you're saying, Ravi, in the final comment. Then it will be handled in same way like explained. We had similar issue and had to eliminate the server from network and had interface issue. Okay, I'm not sure I catch your last statement, Ravi, but I'm not even sure right now if there's another question to it or if that's answered yet. But if there's anything, just post it on the chat again and I'll come back to it. Yeah, so for the servers, you can also mark one of the links to one of the access switches as active. So the other could be a standby link. Ravi, I'm not sure if I've still answered your question, but if it's not, maybe we can come back to it one-on-one as well after the class as well. But yeah, you can rewrite otherwise in the meantime. Sure. Okay, so this is the method that, as we discussed, some of the methods that we use in bridged network topologies to overcome the challenge of flooding. And as a result of flooding and cyclic loops together, the broadcast storm that gets created, you can use VLANs, STPs, and the two of them together to solve the challenge, solve the problem. And this is what most traditional DCNs do. Now, why did with these kind of solutions, the spanning tree protocol, the VLAN, traditional data center network topologies were able to survive and cater to the client server traffic? The topology is not scalable for the modern data center network traffic patterns or the modern applications where we are seeing more of server-server traffic. The reasons are, one, this flood and learn, self-learning model that we saw of the bridges or the switches. This doesn't scale. As data center networks grow, last time we saw a video of a Google data center network where applications that Google has are becoming enormously popular and have so many subscribers that the servers handling the application are going to be huge in numbers, hundreds of them. So as the data center network grows, this flood and learn model of the self-learning switches, this doesn't scale because of the increase in the network size. If I start using VLANs, which is what is one of the solutions we arrived with, the number of VLANs that I can create in a data center network is still limited by the number of VLAN IDs that exist. So if I look at modern data center networks, which are catering to cloud computing environments, and if I try to use a modern data center network with access aggregation core topology, one, the number of servers will be huge. I'll keep on going back to that Google video. Pictorially, we have a picture in mind as to how many servers there were in that Google data center. Thousands of them. Right? So one, the flood and learn model will not scale. If I try to artificially create multiple virtual local area networks, one for each tenant within that data center network, I get limited by the VLAN ID because VLAN ID is a 12-bit field. I can only have 4096 VLANs at the maximum. And if you look at modern cloud compute service providers, 4096 is a very paltry value considering their scale. It's like saying you are limited to only 4096 tenants. You cannot have more than 4096 tenants. That's the maximum number of virtual local area networks that you can create. It's a small number compared to the volume of tenants and number of tenants that a cloud service provider today has. Okay. So the VLAN, one, the self-learning doesn't scale to large topologies. Two, the number of VLANs I can create on these large data center networks is limited by the VLAN ID. Three, the topology brings in a lot of burden on the aggregation switches. Why? So when we say that I have a layer 3 part of the network, which consists of these cores and the aggregation switches, and then an underlying layer 2 part of the network with these aggregation switches being part of the L2 network along with access switches and the servers. What is happening? As external traffic comes in using IP routing, the core switches will receive what? IP routed packets towards a destination IP address. The core will forward that packet to the aggregation switch, which is catering to the destination IP address. Now, how does that happen? So typically, when you receive a packet inside a local area network with an IP address, and when the local area network itself is layer 2 switched, I am unable to recollect if we discussed about this address resolution protocol. I have a vague memory that we did. Can somebody remind me if we did talk about address resolution protocol, where we said the entry point router sends a ARP request, broadcasts an ARP request in the network, asking for the MAC address of the server given a destination IP address. And the write server responds back with its MAC address, and then the layer 2 packet is switched in the layer 2 network, in the local area network, towards the destination. Did we talk about this? I have vague memory that we did. Meanwhile, while you answer my question, I'll reread what Ravi has written. I was referring if a server is flooding with broadcast traffic, then how this situation can be handled, as so far we have seen it's controlled at network configuration level. In my experience, when we found one server was flooding with broadcast messages and we had to remove it from network, and our root cause found that server network interface had issue, physical issue, bad interface. But I'm trying to understand what if has ever flood with broadcast traffic and it doesn't have any interface issue, then how can we control this behavior? So I think, Ravi, the answer to your question would be to enable spanning tree protocol even at the server level, in the layer 2 protocol stack of your server. Okay? If you enable the spanning tree protocol, even in the L2 protocol stack of your server, then the STP will make sure that when you have redundant interfaces configured to the network, one of them will automatically get marked as standby. So the server, when it generates broadcast traffic, it will only send it on the active link, not on the standby interface. That's something you can do. Okay, I don't see the answer to my question. Did we discuss ARP, address resolution protocol? The whole discussion was around what happens when when you have a local area network which is layer 2 switch, which means that packets inside are all being switched or forwarded using destination MAC address. And from outside the network, the gateway router receives an IP packet with a destination IP address. Well, anyway, repeat. I don't remember myself if we talked about it or not. I have vague memory that probably we did, but I am not sure. So when a packet from the internet arrives with the destination IP address for some server, let's say that server is here, the gateway node receiving that IP address packet will broadcast an address resolution request in the network. This is called an ARP request. What is in the ARP request? The ARP request contains the destination IP address, and it's a request to all nodes in the network to check this destination IP address. And if any of them have this IP address, then they need to send back an ARP response with their layer 2 MAC address. Okay, so ARP is a broadcast message that goes to all nodes in the network with the destination IP address, requesting for everyone to check if this is one of their IP addresses, and if yes, then respond back with the L2 MAC address. Now, exactly one of the servers will match this destination IP address. All others will discard the ARP request. This one will respond back to the ARP response, giving its MAC address. And when this gateway router receives the MAC address, it will create a layer 2 frame. Put the destination MAC address so that this packet inside the layer 2 network can be switched to the destination. This is how external IP packets get switched in the local area network, layer 2 switch, to reach the destination. Okay. Now, in the access aggregation core topology, the core switch, the core router, what do we have? We have now two networks. as part of the local area network. One is layer 2 switched, the other is layer 3 routed. This is the core router. This is the aggregation switch, which is actually a switch cum router. Okay? And then you have access switches inside and the final servers. Now let's say an IP packet comes to the core with an IP address of server A, destination IP address of A. Right? This is A. The core will send an ARP request towards the layer 2 network. The aggregation switches are required to respond back to this core giving their own MAC address. Right? This is called proxy ARP. It is done so that all packets which are coming from outside the internet are forwarded to the aggregation switches, and then the aggregation switches can themselves handle the ARP functionality inside the L2 network in order to forward the traffic towards the right server. This function will introduce a lot of additional burden because it's acting as an adaptation switch in between the core and the final servers. It puts in a lot of burden on the aggregation switches to be able to respond to all ARP messages on behalf of all the servers inside the layer 2 network by using the proxy ARP functionality. So essentially, we are saying that the aggregation switches will have to be some special purpose, high-end switches, more bulkier, more computationally powerful than the access switches in order to be able to handle this kind of a burden. What it results is skewed or asymmetric network topology. What do I mean by asymmetric network topology? It means that not all switches in your network topology are of the same type. Some switches, like the access switches, can be computationally less complex with lesser number of switching ports, whereas aggregation switches probably need more number of ports because they're aggregating traffic from multiple access switches, but they also need to be computationally more evolved and enhanced because they have the extra burden to respond to all these ARP messages coming from the core routers. So that we will say why that is a challenge, right? It is a challenge because it leads to asymmetric network topologies, which when we come to modern topologies, we'll see that modern network topologies are more symmetric in nature, and we'll talk about the benefits of symmetric topologies. But for now, just note that these access aggregation core topologies, they are more asymmetric in nature. Asymmetric in the sense that the type of switches that exist are not all homogeneous. They're not all of the same type. Okay, they are of different capacities and different scale. Fourth, while the STP protocol is defined to cater to network faults. So we said one of the principles of the STP is to translate a network graph into a network tree. But when there's a fault in the network tree, some link goes down, the STP has to function again to identify an alternate route to the failed node or the failed communication link. So it has to relook at the network graph and recreate a spanning tree by using some of the standby links to create a new spanning tree. Now, when you look at modern data center networks and the kind of applications, this spanning tree is going to become a very important thing because there is more of server-server traffic, more of east-west traffic. So eventually you will see, because there are a lot of servers and a lot of server-server traffic, your data center network is horizontally very large. And therefore, there are a lot of these aggregation switches which are handling the horizontal span of the data center network. Now, when the STP protocol works in this kind of a horizontally elongated and large data center, where there are a lot of aggregation switches, lot of underlying access switches being connected to these aggregation switches, a lot of redundancy. STP itself has been observed. Ravi, it's similar to something you were saying. The protocol itself has sometimes been known to have unpredictable behaviors. Okay. And this unpredictable behavior often emerges in larger networks when there are some random and frequent node or link failures. Okay. So when a link fails or a node fails, let's say an access switch fails, STP has to come up again, look at the entire network graph, identify alternate routes, create a new spanning tree. While it is in the process of doing that, let's say a couple of more nodes failed. And STP has to now rework in the middle of something it was doing. In certain such situations, when you see multiple faults happening one after the other in large size networks, STP often, what should I say? I mean, think of it like having some bugs in the protocol itself, that it eventually lands up into defining certain unpredictable and unusable topology. So this is what network administrators have observed by experience. In large scale data centers, when you have a lot of aggregation switches and a lot of access switches, a lot of redundant links, and then some multiple faults happen one after the other, STP sometimes cannot address it, ends up giving you certain unpredictable, unusable topologies, and then manual administrator intervention is needed to sort out the situation. Okay. So these kind of observations are common with STP. It's not a completely foolproof protocol that works with all kind of situations all the time. Okay. So these are some of the challenges that have been observed in traditional data center networks as their scale evolves and as the traffic pattern evolves to the modern data center network scale and modern data center network traffic, which is more server-server traffic. So, okay, when you look at the complexity of a traditional access aggregation core network, we see that the amount of oversubscription of network bandwidth that I need in an access aggregation core network also needs a careful design. Why? See, we said there's a challenge of a broadcast town in an access aggregation core network approach, because of which I needed to bring in STP, spanning tree protocol. Now, when spanning tree protocol comes in, it does not use some of the available links and the available bandwidth. It marks them as standby. So though it is like saying that network bandwidth has become unusable. So the remaining active links must have enough bandwidth so that they can handle or address or cater to all the server-server traffic that is supposed to flow in the network. And therefore, I have to carefully design the bandwidth of these links, or in other words, oversubscribe the network bandwidth of each of these links so that when STP marks some of them as unusable, the remaining available active link must still be able to handle the entire network traffic load without leading to congestion. So in other words, if I rephrase, I'm saying we need a lot of more oversubscription of network bandwidth so that congestion does not easily occur when I use STP protocol in the access aggregation core topology, where STP has the effect of marking some of the links network bandwidth as unusable. See, if all links were possible to use, I would have distributed on, this is what we call as network load balancing. We would have balanced our network traffic across all these links. And even with little oversubscription of network bandwidth, I would have been able to cater to the server-server traffic. But with STP coming in and marking some of the links as unusable, my entire burden gets put onto the only few active links. And therefore, those active links have to be oversubscribed with network bandwidth if I want network congestion to be avoided. If I don't do that, then congestion can quite easily occur in an access aggregation core topology. So that's another challenge or issue with access aggregation core topologies used with STP, is that you need to oversubscribe network bandwidth many factors more than what you would normally do in a modern data center network topology. Third thing is the blast radius of access aggregation core network topologies, right? So when we talk to blast radius, the term comes from the conventional use of the term blast. Right? If you have an explosive device, a bomb, which blasts, right? Typically the impact of an explosive device is measured by the radius of the impact of that explosive device. If there's a bomb blast and you say that the sharpeners flew to 1 kilometer radius, the sound impact leading to glass breaking was felt up to 6 kilometers. That's what measures your intensity of the blast. Okay? Similarly, networks, when we measure the failure impact, the impact of a network failure, we measure it similarly by measuring what we call as the network blast radius. So we say if there's a single failure in the network, what is the impact of that on the overall network? Okay, that's what we mean by the blast radius. Now, in access aggregation core topologies, network failures result in very coarse-grained failures. Right? Or in other words, the failures have a very large blast radius. Can you guess why that is the case? By just having an understanding of the topology that we just discussed. Why do you think an access aggregation core topology has a larger blast radius? I mean, it's basically another way of saying that if there's a single failure, one failure in the network, the impact is much larger. The blast radius is much larger. The reason why we say that is because of the 1:1 redundancy that is used in the access aggregation code. So because everything is 1:1 redundant, any failure halves the available bandwidth. A link failure halves the total available bandwidth in the network. An access switch failure reduces half the connectivity links of the network. So because of this kind of a topology, which says that the access aggregation core topology has a very high blast radius, one failure results in a very large part of the network or a very large bandwidth of the network becoming unusable. It has a large blast radius. Lastly, the way I explained on the previous slide, the constraint of using VLANs with STP together, where I said that if I have to use efficiently the entire network bandwidth of an access aggregation core data center network, I have to build my VLANs and the spanning trees in such a fashion that VLAN 1 creates one spanning tree, VLAN 2 creates another spanning tree, subject to the constraint that these two spanning trees use mutually exclusive redundant links. So that in a way, we are balancing the load across the redundant links of the network and thereby utilizing all the network links. But this constraint that we are introducing, what is it causing? It's introducing inflexibility in the topology of the network. Right? I'm basically saying that it's not possible to have the same VLAN to be present across two different pairs of aggregate switches. They have to be mutually exclusive. It's introducing constraint in the network topology, resulting in inflexibility in the network. So access aggregation core topology, while it works reasonably okay with your client server traffic, it has those benefits which we talked. It's low cost, it's fast, it's zero configuration. There are challenges when it scales, when it grows to the size of a modern data center network with thousands of servers. As it grows horizontally, flood and learn model doesn't work. It doesn't scale. VLAN causes a problem because you have only 4096 virtual networks that you can create out of it. Aggregation switches get a lot of burden. Spanning tree protocol starts to show you unpredictable behaviors. Oversubscription of bandwidth grows to phenomenally high levels. Failures start showing large blast radiuses, and the network overall becomes highly inflexible. 7 or 8 problems that you see with access aggregation core topologies as you scale the network to more servers and more switches. Okay. So what is the solution to this problem? How do you scale? My problem is I have to scale the network horizontally, grow the network, more servers. How do I scale that network to a topology which can overcome the challenges of the access aggregation core? What are my learnings from the internet? The internet is a large scale network, especially when I look at the core of the internet, the backbone of the internet. The backbone of the internet is connecting these thousands and tens of thousands of smaller ISP networks together. How does it work? What is the topology which makes it work, even if such large scale horizontal spread? Can I learn something from there and utilize it in a data center network? Okay. So the answer came from two the answer to this challenge, which access aggregation core had, which we discussed on the previous slide, came from two sources. One part of it comes from how telephony networks are designed to be always non-congested. And I say non-congested, see, in telephony networks, these are circuit switch networks. So when we talked about our network fundamentals part, we discussed what is the difference between a circuit switch network and a packet switch network. We said a circuit switch network always has a reserved path created from a source to the destination even before data transfer starts. So in a telephony network, I dial a number for a destination. Before I can start talking, there is some control plane protocols that run to establish that circuit end to end. As part of that circuit establishment, the network path gets established. Resources along the path get reserved. And now there are reserved resources for all my data to be transferred from the source to the destination. So congestion will never occur. Essentially, we say that there is a process of call admission control. I admit a call in a circuit switch network only when there are enough bandwidth or resources to cater to the traffic of that call. If I don't have resources to cater to the traffic of that call, I do not admit that call. I rather give the person a message, all routes on this network are busy or the network is busy, please try after some time. I don't admit the call, but if I admit a call, I make sure that there are enough resources from the source to the destination. A complete data path is set up. Network resources are reserved on that path. Essentially, we say we've created a circuit. That's what it's a difference to a packet switch network. Now, in a telephony network that's designed as a circuit switch network, how do I want to design the network itself? I have to design the network in such a fashion that I always have a route. When I say route, a path from any node S, which is the source, to any telephone D in the network, so that I don't end up losing revenue. I don't have to say all routes on the network are busy, please try after some time. I don't want that because it's loss of revenue. Right? I want to maximize on the number of calls that can get through my network. In other words, I'm saying I want to create a network topology such that telephone to telephone calls can be maximized. Now, if I look at one telephone as a server and the other telephone also as a server connected via a circuit switch telephony network, what does it translate to? A telephony network is nothing but a huge volume of server to server traffic, isn't it? Right? So if I look at a pure telephony network, there's a lot of telephone to telephone traffic, which is nothing but like a server to server traffic. I have to maximize the server to server traffic so that I can maximize the revenue of based on the calls that I'm establishing in my network. And therefore, I need a topology which can cater to the maximum number of such server to server calls. Okay, this is the challenge which was existing in circuit switch network, which was solved by uh, 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 an inventor called Charles Claus, and the topology which he designed got to be known as the Claus network topology. Okay, so let's try to understand what is the basic Claus network topology and how is it used in a modern data center network. Okay, for now we will focus on a specific type of Claus topology which is called the leaf spine topology, and then I'll first talk about the simpler Claus topology called the leaf spine topology. And then I'll take you to the classic Claus topology, which actually Charles Claus had proposed for the telephony network. Okay, we'll come to that next. But let's look at the simpler basic Claus topology called the Claus leaf spine topology, which is used in our modern data centers as the building block of the modern data center. So what do you have? You once again have the physical servers, rack servers, just like we had in the access aggregation core. I've taken same example. So we have 12 servers. Once again, 12 physical servers across 4 racks. The same example as we have. Now, instead of having access switches, I have now replaced them with a new type of switches that I'm calling as leaf switches. Okay. These leaf switches are actually part of the rack. You have a rack of servers. In the top shelf of the rack, you put a switch called the leaf switch. Now, because this leaf switch goes in the top of the rack, in the top shelf of the rack, this leaf is also a lot of times in literature called the TOR switch. Have you come across this term? The TOR switch. The TOR is an acronym used for top of rack. Okay, so it's part of the rack itself. It's top of the rack switch. Now, what does this top of the rack switch do? it has a very neat rack level cabling. We normally call it the backplane of the rack. Using the backplane of the rack, you have very neatly laid out cables that connect each of the server to the leaf switch, which exists on the top shelf of the rack. So you have now a very neat configuration, very well cabled, neat, using a cabled backplane in the rack itself, where the cables from the servers are going and landing up in some ports of the leaf switch. Okay, so every rack is nothing but a set of servers and a top of rack leaf switch. Now, the leaf switches, they are all L3 switches. This is one big difference from the access switches of the access aggregation core. The access aggregation core were all L2 switches. Whereas in the leaf spine topology, all leaf switches are actually layer 3 switches. When I say layer 3 switches, they can switch traffic at layer 2. So if one server in the, let's say A, wants to send traffic to B in the same rack, yes, this leaf switch is capable of routing it via the backplane using MAC address, can do L2 switching. But it also has a layer 3 routing functionality built in, which means if a server A wants to send traffic to another server C using an IP address, the leaf switches can also act as IP routers. So we call them layer 3 switches, L3 switches. They have L2 switching functionality as well as layer 3 routing functionality. Okay. Now these leaf switches connect to a second tier of switches called the spine. And spine switches are also layer 3 switches, just like the leaf switches are. The topology is such that every leaf connects to every other spine. Okay, creating a kind of a mesh topology between leaves and spines. Most importantly, the leaf and the spine switches are of the same type. There is no distinction between the spine or the leaf switch. You can take a leaf switch, make it a spine, take a spine, make it a leaf. They are of the same type and make and configuration. It's all exactly the same. It's unlike aggregation switches, which were required to be bulkier, more complex, different kind of switches. No, these 10 spines are all of the same type. And they are all connected together using a mesh kind of a configuration, creating a meshed layer 3 network amongst them. Both of them are layer 3 switches, so they're creating a layer 3 mesh network amongst them. This is the second input which I said came into this topology. This is very much like the core topology of your internet. Think of the spine like your tier 1 tier ISPs and your leaves as your access ISPs. Then most of the times your access ISPs connect to all the tier 1 ISPs that are available to create a redundant internet core, the backbone of the internet. That is the topology you brought in to the data center. Okay. Now, what is the benefit of doing that? So I've just said what is it, but what is the benefit of doing that? Okay. So we said each leaf connects to every other spine node. And the consequence of this is that a spine connects the leaves to one another, every spine, if you look at it, because every leaf is connected to every spine. If you take one spine, it connects all leaves to one another. Okay? And okay, this I've already said. Leaf is the top of the rack switch. Leaf and spine switches are of the same type, so they are interchangeable. They can be replaced with each other. Now, what is the benefit of this leaf spine topology? One of the biggest benefits that this topology brings in is the ability to use homogeneous switching equipment. When you look at a modern data center network, the reason in the previous class I showed you that YouTube video is because I always wanted you to carry that picture of a large scale data center network like Google has. The volume of servers that it has, the number of racks that exist in that data center. Do you think it's easy for a network administrator to manage different types of switching equipment when setting up a huge network like the data center network with tens of thousands of servers in thousands of racks inside the data center? You think it's easy to manage multiple different types of switching equipment? It's not. As soon as you say that all my switching elements are of the same type, it brings down the complexity of your network many folds. One, it requires your personnel, the network administrators, to be trained on only one type of equipment. Two, it means you can benefit from economies of scale. When you go to market to purchase the switching equipment, you are purchasing thousands of them of the same type. Three, it simplifies your network management. If you have a failure, you don't have to think of, do I need to replace this switch with type A switch, type B switch, type C switch, type D switch? They're all of the same type. I just go to my repository of free line switches, get one day from there, replace it with the failed switch. So easy to manage a network where you have homogeneous switching equipment. One of the benefits of leaf-spine topology. Two, this topology has an enormous amount of redundancy, and a consequence, it reduces the blast radius. Unlike 1:1 redundancy in the access aggregation core, where one set failure meant half the network's gone, large blast radius. Here, what do you see in the topology? If there are n spine switches, there is actually n:1 redundancy. There are n paths between any switch to any router. Sorry, any server to any other server. So the redundancy has gone up many folds. There are more than two paths between any two servers. No, there is no challenge of broadcast storm or cyclic paths getting formed, or me to having introduced spanning tree protocol to do away with the redundant link. Why? Because this is a layer 3 routed network. What do we know about a routed network? A routed network takes care of cycles. When you determine the route to be taken from a node A to a node B, cycles don't, you have a network topology. If, talk about Dijkstra's algorithm that we talked about. The network graph has cycles in the path. But when the Dijkstra's algorithm finds the shortest path from a source to a destination, it determines an acyclic route to the destination. So in a routed network, a layer 3 network, like the core of the internet or the rest of the internet, cycles are automatically taken care of by the routing protocols. So I can utilize multiple paths between multiple servers. Some servers could be using some paths for communication. A pair of server could be using one path through the network. Another pair of server could be using a different path through the network. A third pair of servers could be using a third path through the network. So I don't have to introduce artificial constraints into setting up VLANs and STPs in a constrained fashion such that all my network bandwidth is being utilized without having cyclic paths and all those things. The internet naturally solves that problem by using routing as the way of forwarding traffic. And that's what I'm doing in the modern data center network. Not only am I having a lot of redundancy between servers, I'm doing away with the challenge of cyclic paths. I'm utilizing the entire network bandwidth while allowing the routing protocols determine what the best path is between any two servers. Okay? The network, resulting network, is a high capacity network. Why is it high capacity network? Because let's say I have to oversubscribe network bandwidth. See, there's a lot of, if I realize there's a lot of server traffic going on. And earlier, the server traffic was X megabits per second or terabits per second or petabytes per second, whatever it is. Eventually, over a period of time, I've realized that it has gone to X into 1.25. It has grown petabytes per second. What can I do? How can I oversubscribe the network bandwidth? I can scale horizontally. I don't need to change the bandwidth on every individual communication link that exists in the network. Do you think I'm going to go and change the bandwidth on each of these links if I have to oversubscribe bandwidth from X to 1.25X? No, I don't need to do that. The existing links can remain the way they are. How do I oversubscribe network bandwidth? I add more spine nodes to the network. When I add more spine nodes, I add connectivity links between the leaf nodes to those spine nodes, effectively increasing the network bandwidth. But what is the network bandwidth? If I have to say what is the network bandwidth between any pair of servers, think of this as a cloud. See, every spine connects to every other switch. The collective bandwidth of all these interconnected links is the network bandwidth. Now, if I have to increase the network bandwidth, I don't have to increase the bandwidth of each of these individual communication links. I don't have to change the copper cables with the fiber optic cables, grow their bandwidth. No, I'll just go ahead and add a few more spine nodes and connect the leaf using the same kind of communication links to these new spine nodes as well. My cross-sectional bandwidth of the network has grown. This is what we call as a scale-out architecture. We can horizontally scale without touching the existing equipment, without touching the existing communication network bandwidth. It scales horizontally. So I can add spines if I have to increase the capacity between leaf nodes. Okay. The network is very simple. Spines only connect to leaves. They are not required to have any other additional functionality like R. Why? Because all of them are layer 3 switches. So all the layer 3 network functions like routing protocols, layer 2 switching, layer 3 routing, it's supported by the edge switches as well. The leaf switches support this functionality. So there is no additional load on the spine switches. And because there is no additional load on the spine switches, they don't have to be of the special type of, like, unlike aggregation switches. They can be same type as leaf switches. Okay. So the underlying interconnect model that we use in the modern data center with a leaf spine topology is routing. Routing is the interconnect model that we use instead of layer 2 switching. Okay. Also, what we do in most data center networks is to augment the general routing protocols like RIP or OSPF or BGP, which we will talk about in a later class. We augment it with another routing protocol called ECMP. What is ECMP? ECMP is a protocol that can be used complementarily alongside other routing protocols. It's called equal cost multipath protocol. So in general, what does OSPF do? OSPF runs the Dijkstra's algorithm. So given a network graph, it will find the lowest cost path between a source and a destination. That's what Dijkstra's algorithm does. That's what OSPF relies on. But what if there are multiple equal cost paths through the network? Normally, OSPF will just pick one of them. But when OSPF is used in conjunction with ECMP, Equal Cost Multipath Protocol, ECMP will make sure that if there are multiple equal cost paths from source to destination, then the traffic generated from the source gets load distributed across these paths. That's what ECMP as a protocol does, Equal Cost Multipath Protocol. So in these leaf-spine, along with the leaf-spine topology, routing plays a very important role as the interconnect protocol with the general routing protocols augmented with ECMP, Equal Cost Multipath Protocol, thereby enabling load balancing across multiple equal cost paths through the network. Okay, sorry, I didn't realize I was already 4 minutes above the class time. I'll just take one more minute and maybe I'll close this slide and then we will talk more about it next class. So essentially we are saying that class topologies are highly scalable network topologies. We call the class topology as a scale out architecture. It's a scale out architecture because when I have to add more servers, because I need more computational power. See, my YouTube traffic is growing in the Google network. So what do I need? I need more YouTube servers to handle the incoming traffic. I add more servers. When I add more servers, it's basically adding more racks. When I add more racks, there are more top of rack switches getting added. So more leaves are getting added. So essentially in the topology, I'm scaling it horizontally. I'm adding more leaves and more servers in order to increase the computational capacity of my data center network. So to add to the computational capacity of my network, I add more leaf switches and more servers. If I have to add more to the network bandwidth, I add more spines, like we talked a little earlier. So adding leaves increases my ability to add more servers. Adding spines increases my ability to have more bandwidth in the network, thereby increasing the ability to handle server-server traffic. It's completely a scale-out architecture. That's what class topology brings to the table. Okay, so we'll pause here today, and next class we'll talk about the classic class topology, which Charles Claus defined. How does it boil down to the leaf-spine topology? And how do we use this topology in modern data center networks as a building block to grow the data center networks to unimaginable sizes and server numbers? Okay, that's what we will talk about next time. And also next time, then we will look at the journey. So what, as I said, today we looked at access aggregation core and these class topology, the first step and the last. Next time, we will traverse through this journey from traditional to modern and how intermediate technologies came in. What did they solve? What problems they brought in? How did we reach this endpoint? And so that's also something we will talk about next class. Yeah, Ravi, thanks for reminding me. Next weekend, which is 5th October, will be your makeup exam. So we don't have a class. When I say next class, we'll actually meet on 12th of October. Okay. So 12th of October is when we'll meet again and continue from here. So thank you everyone for joining in. Have a good exam for all those who are taking a makeup exam. And see you again on 12th October. Thank you. Bye-bye.